Hey, GeoTrekkers, this is Dr. Hal. If you've been following extreme weather around the world, the big story, possibly the biggest story on the planet this winter, has been what's going on in the western U.S., especially California. Atmospheric river after atmospheric river pounding the West Coast, mega snow up high, and even really snow at lower elevations where they weren't used to it. And then a lot of flooding happened during the winter, and we're expecting a huge flood season as we move in through the spring and even early summer. I like to travel quarterly, go out to really where big extreme weather is happening or natural disasters. It was a no-brainer that I had to come out to the West Coast and see this for myself. I came out for 12 days in March to California and Nevada. It was really indescribable. I've lived in Alaska for 3 years, and I've never seen these kind of snow totals. 15 to 20 feet of snowpack above the ground, snow loads on roofs that are ridiculous, roofs collapsing, just all kinds of things that are, people tunneling to get into their homes, really storm after storm over many months, record-breaking snowpack in some places, and a lot of concern with flooding over the next several months. So this is really a no-brainer that we had to cover this with a podcast, and there's so much content here. We're actually going to do 2 different consecutive podcasts just to cover this. So the first one, we're going to really have academic perspectives of the California mega winter. We have 3 academic heavyweights that are going to come on the podcast this week to talk to us about their perspectives of what happened, why it happened, how we can better understand this, and really just get a grasp of the science behind this. If you're watching the video feed for this, yes, those are 12-foot icicles behind me. I'm recording this at a German lodge up by Lake Tahoe. It just snowed, I guess, another 8 or 9 inches today. Who's even counting anymore? Well, we'll tell you who's counting. Andrew Schwartz is counting over at the Central Sierra Snow Lab, and he's one of the 3 academics we have on the show today. This is going to be a fun one, and you're going to learn a lot. I know a lot of people are really interested in this story because California is the most populated state in the U.S. The impacts are tremendous whenever anything happens out here. If you're new to the podcast, GeoTrek explores the world to find stories that are not covered in the mainstream media about extreme weather and natural disasters. We try to do 3 things. We focus on the physical aspects of those disasters and the science behind why they're happening. Number 2, we look at the impacts of these extreme weather events and natural disasters. And then finally, we look at ways that we can get out ahead of these things, mitigate them, and reduce losses to save lives and property. On the podcast this week, we have 3 academic heavyweights. We have Daniel Swain from UCLA and Weather West. We have Andrew Schwartz from the UC Berkeley Central Sierra Snow Lab, and then Julie Kalansky, who's at the Scripps Institute for Oceanography. They're all going to weigh in, and it's going to be a great discussion here on the podcast this week. Our first guest this week is Daniel Swain, climate scientist at UCLA's Institute of the Environment and Sustainability. He's also a blogger at Weather West. Their focus is California weather and climate perspectives. He has done a lot of work in Colorado and California and a lot of states out west. We're really thankful to have him on the podcast to explain the regional climatology and what happened this winter out west. Daniel, thank you so much for taking time to come on the GeoTrek podcast.
Yeah, thanks for having me.
Daniel, everyone's been talking about atmospheric rivers this winter. It's been a very active weather pattern in the West. What exactly is an atmospheric river?
Well, simply put, an atmospheric river is a thin filament of moisture in the atmosphere moving quickly above your head. So essentially, it's a whole bunch of water vapor in flux in the air. And these rivers can carry, these sky rivers can carry every bit as much of water as a major terrestrial traditional river. In fact, the largest atmospheric rivers carry more water than something like 20 or 25 Mississippis. So there's a tremendous amount of water in the air in these atmospheric rivers that can eventually fall out of the sky as precipitation, as rain and snow. So these can be really consequentially important features, both for delivering water supply on the beneficial side of things, but also for flood risk in places where they're prevalent.
Yeah, that's a lot of moisture, and that explains maybe why we're having so much snow and the big flood risk in California and many of the western states as well.
Yeah, that's right. This year we've seen an unusually high number of atmospheric rivers in California, and that is exactly the kind of thing that you tend to see in wet and flood years in California and along much of the west coast of North America. They are the flood generating mechanism along the west coast. These are the types of storms that bring the most rainfall. Absence of atmospheric rivers means drought. That's what California's been experiencing more often this decade, is not enough atmospheric rivers. But now this year, we've seen an overabundance of atmospheric rivers. And so now we're sort of slipping into the opposite problem there with water overabundance and flooding.
Daniel, many different atmospheric phenomena, like whether it's a blizzard, a hurricane, a lot of times there are very specific criteria, like, was there a hurricane or not? We know exactly. With atmospheric rivers, are there specific criteria that define if one formed or not, or is it more subjective than that?
Yeah, that's actually a good question. And there's an entire research endeavor called the ARTMIP project. It's an acronym that stands for the Atmospheric River Intercomparison Project. Essentially, there's a bunch of different ways we can define atmospheric rivers. There's a whole suite, a whole portfolio of different formal scientific definitions that give you somewhat different answers regarding exactly what an atmospheric river is, and therefore how many there are. Using one algorithm, you might say there were 18 this winter. Using another algorithm, you might say that there were 12. Another still might say that there were 9. So it depends how strict you are. And so it does matter definitionally. There's an interesting debate, I think, in the meteorology community, whether all atmospheric rivers as currently defined are truly distinct from a certain aspect of a traditional winter storm. So there's something known as the warm conveyor belt in mid-latitude cyclones. Mid-latitude cyclones just being ordinary winter storms, essentially. And there are atmospheric river-like features in these warm conveyor belts of extratropical cyclones. But I think the consensus at this point is generally that atmospheric rivers truly are distinct, at least by certain definitions, because they can exist in the absence of a parent storm system. So you can sometimes find disembodied atmospheric rivers, if you will, stretching out over the subtropical Pacific Ocean, for example, where there are no storms. And so I think that would at least suggest that you don't need a parent storm to generate them and that they are truly distinct. And so it is true, though, that atmospheric rivers have their greatest impacts and have the most potential to bring extreme weather in the form of heavy precipitation and strong winds when they do come associated with parent low pressure systems. And so it's often these low pressure systems that bring the upward vertical motion in the atmosphere necessary to squeeze all that precipitation out as intense rainfall or heavy snow. So there is definitely an interaction between atmospheric rivers and low pressure systems, winter storms, and they are synergistic. So each can strengthen the other. And it's sort of bidirectional. So the stronger the atmospheric river, sometimes the stronger the low pressure system, and vice versa. So that's what we've seen a lot of this year, are low pressure systems and atmospheric rivers together in California that have produced a bit of chaos.
Yeah, and these atmospheric rivers, they can go out. I mean, they're linear features, right? They can go out for hundreds or even thousands of miles out over the Pacific, right?
Oh yeah, it's quite common. In fact, most atmospheric rivers, by definition, actually, are usually at least a couple thousand kilometers or a couple thousand miles long. So these are very long, narrow features. They really do look like rivers. If you look at them from a 2D perspective, like from an Earth orbiting satellite or something looking down, they do look an awful lot like terrestrial rivers. They can wind around a bit. They don't have quite as many bends as, say, a meandering river might have. They are straighter than that, but in general, I mean, there are these very long, narrow features that can extend all the way. I mean, some of the atmospheric rivers this winter, for example, these would be known as the quote unquote Pineapple Express variety, the ones that have origins in the subtropics near Hawaii, hence pineapples. Extend essentially from the Hawaiian Islands to California. That's not a short distance. I mean, that's a long plane flight to get from LA to Honolulu, and yet this moisture transport, the atmosphere is moving, in some cases, moving that water from the subtropics to the mid latitudes. So that's these features are large, but they are, the spatial dimension is that they are dramatically longer than they are wide, and so they are these filamentary features. There's always a few of them somewhere on Earth. There's always atmospheric rivers out there, but they aren't always affecting populated land areas. Oftentimes they'll be out over open ocean basins where they aren't doing anything too exciting.
Well, that's right. And the impacts this year are so huge because they're really affecting our most populated state. So obviously seeing a lot of snow, seeing a lot of rain impacts. I wanted to ask you as well, does climatology exist as far as an average annual amount of atmospheric rivers impacting the West Coast? Does that kind of climatology exist?
Yes, but it's really variable. This is the main thing that drives interannual variation in precipitation along the West Coast, are variation in the numbers of atmospheric rivers. As I mentioned, if you're in a drought along the West Coast, it's because you haven't had enough atmospheric rivers. If you're having a flood, it's because you've either had too many atmospheric rivers or too intense of atmospheric rivers. So they really are the driver in this part of the world where there is not very much warm season precipitation. So we don't get hurricanes, we don't get summer thunderstorms. It's winter cool season precipitation, and that is it, which makes it quite different from the rest of North America and really most of the rest of the world, where it rains in summer. It does not really rain in summer along the West Coast. And so it's sort of boom or bust with an atmospheric river climatology. You either get enough or you get too many, or you don't get enough in the winter. And that really dictates drought or flood. But things like El Nino and La Nina can modulate. This year is actually a bad example of it because it's a La Nina year that kind of looks like an El Nino year in terms of atmospheric river climatology. So ignore this year if you want to know the long-standing relationship. But in general, things like El Nino and La Nina, tropical ocean temperature cycles, changes in the Pacific Ocean temperature patterns, the changes in the Earth's stratosphere even. All of these can result in variations in where these atmospheric rivers make landfall, and therefore how frequently you get atmospheric rivers in a given segment of coastline. And they can vary from week to week within a season. Certainly within seasons, we see way more of them in winter than we do in summer. And then year to year as well. Some years there's a lot of atmospheric rivers in one place, and other years there's very few.
Well, Daniel, let's talk a little bit about those climate controls, those teleconnections. I mean, in general, long term, what would be the type of setups where we would typically see more atmospheric rivers? For example, would we typically see more during an El Nino year? I mean, what would be those atmospheric controls in general long term?
Yeah, I mean, it really depends where you are, and because it often has the opposite signal. So if you're in California versus, say, Washington State, for example, El Nino in California might generally mean, especially in Southern California, might mean more and stronger atmospheric rivers. And in Washington, that might, on average, mean fewer and weaker atmospheric rivers. The reverse would be true with La Nina. Of course, El Nino is a warming of the tropical Pacific Ocean, eastern tropical Pacific Ocean, and La Nina is a cooling of the eastern tropical Pacific Ocean. But there are, of course, major exceptions, this year being one of them. This was a La Nina year where the pattern looked an awful lot like El Nino, where there were not that many atmospheric rivers in the Pacific Northwest, and there were a ton in California. So that is the opposite of the traditional pattern, which indicates that El Nino and La Nina are not the only factors at play, and that sometimes it's difficult. We don't have a great deal of predictability at seasonal scale. So this winter, the prediction, now granted, the seasonal predictions are always a probabilistic tilt in the odd forecast. They're not explicit weather predictions, but the prediction this season for California was an elevated likelihood of a drier than average winter because of a strong La Nina event. Clearly, that did not happen, and it did not happen because we got a bunch of atmospheric rivers right when we thought that we might get not enough atmospheric rivers. So something else happened this year, and as of this conversation, I can't tell you exactly what that was. Maybe we'll understand it better in retrospect, but it's just a nice indication that there's a lot of other kinds of variability in the atmosphere that are important beyond El Nino and La Nina as well.
It reminds me a bit, last year we were expecting a very active hurricane season and didn't really get it, and it reminded us there are other controls like Saharan dust and all these other things. The atmosphere is complex. There are a lot of moving parts. And so it sounds like with this, the odds were stacked towards a more dry winter, but we didn't get it because of maybe other things at play.
Yeah, I mean, and I think we may be able to figure out what it was in retrospect, but the question is, what was the thing that caused this predictable in advance or not, or is it only something we can recognize, like the Saharan air layer or the Atlantic? Is there only something we can recognize once it happens, and they say, okay, well, obviously that's what happened, like, great, but could we have known that was going to happen from the outset? And the answer is maybe, maybe not. It kind of depends what it was. So
I picture a lot of PhDs maybe being done on this type of setup, this type of winter, right? Because of such a big impact.
I do think that there will be studies specifically on this winter in California, given that it was a high impact winter, has been, continues to be, and was not well predicted from the outset. So it's a good candidate for trying to figure out if you want to study what are we missing and how do we improve forecasts. This year would be a good year to try and figure out what we missed, because clearly there was something. The question is whether it was a predictable something. And I kind of hope it was, but maybe it isn't. And I guess we'll find out.
Yeah, no, that's a great perspective. In other words, is it something that could be predicted ahead of time for future seasons, or was it kind of random and not predictable?
Yeah, I mean, there's even some speculation this year that the massive undersea volcanic eruption, the Hungatanga eruption last spring or last winter, which injected a record amount of water vapor into the stratosphere and had the opposite effect on climate that volcanic eruptions often do. We're more used to in the 20th century volcanic eruptions resulting in temporary cooling because it emits a bunch of sulfur aerosols into the stratosphere, sort of shades the Earth for a year or two and shaves off a fraction of a degree of temperature from the global mean. This volcano did not do that. It emitted very little sulfur aerosols into the stratosphere and instead added a greenhouse gas, water vapor, into the stratosphere and resulted in at least a transient period of planetary warming. So that may have really thrown us all for a loop. No one really knows yet exactly what the regional effects were, but it definitely had some global effects. So
Yeah.
could it have been a volcanic eruption that we couldn't have predicted in advance? Maybe. Maybe it wasn't that at all. Maybe it was something more mundane or something that was, weird in the Pacific Ocean. But I'm curious to find out. About a year from now, I think we'll see a bunch of studies.
You're making our listeners scratch their head, and you're reminding us how interconnected everything is, which is great. Something we talk about a lot on this podcast. Daniel, everybody's asking me what happens when all this snow melts. I mean, what does the flood risk look like? Do you have any insights on that as we move through this upcoming spring?
Yeah, I mean, so the rainy season should start to taper off pretty soon in California. I mean, the peak is winter, the spring is kind of the shoulder season. It can still be fairly wet in spring some years, but in general, the amount of precipitation that falls in California moving forward from April is a lot less than you'd get in winter. So I think that the likelihood of flooding in places that don't see snowmelt is just decreasing, fortunately. I think that we're largely out of the woods in places that don't have a huge snowpack upstream. The problem is there are some really vulnerable places that have an enormous snowpack upstream. In fact, in the case of the southern Sierra Nevada, a record-breaking snowpack. It is genuinely remarkable that this is the largest snowpack that we've ever recorded in the southern Sierra Nevada. And all of that water is eventually going to have to come downhill. Most of it will melt on the west slopes of the Sierra. Some of it will melt on the eastern slopes and cause potential flood risk in like the Owens Valley and in some of the watersheds that drain to the Great Basin. But the really big concern right now is the bulk of that water that's eventually going to drain into the California Central Valley, in particular the southern half of the Central Valley, the San Joaquin Valley, and the Tulare Lake Basin, which is already flooding. And used to be, before it was pumped out and intensively farmed, as a few small towns exist within the lake bed, the ancient lake bed, used to be the largest freshwater lake west of the Mississippi. And in a year like this one, the geography may dictate that it becomes once again the largest freshwater lake west of the Mississippi. Of course, the problem with that is there's a lot of things in the way now. It's not an undisturbed environment. So the intersection of these low-income farm-working communities, these very extensive agricultural lands, this is going to be a major collision course for a lot of the snowmelt coming downhill over the next few weeks and through really between now and about the end of May or so, early June. So there is major flood risk in the San Joaquin Valley. And then also downstream. Downstream in this case is actually further north. So the Southern Sierra, the San Joaquin River eventually runs from south to north for a little while until it enters the San Francisco Bay Delta. So really from about the San Francisco Bay Delta south, there is a major risk of snowmelt-related flooding this spring. And it's not really a question of whether there's going to be flooding. It's more of a question of how severe that flooding becomes. Does it melt all at once and cause really widespread, serious flooding? Does it melt more gradually, and is it somewhat more manageable, although there will still be significant flooding because, frankly, there already is in some places? That remains to be seen. But if we got a late season warm atmospheric river, for example, and that warm humid air mass quickly melted a lot of the snow, that would be a big problem. Or the opposite, if we quickly ended our rain season and transitioned immediately towards an early spring heat wave, that would also be a big problem at this point. So there's a decent chance of just clear day, sunny sky flooding now in the southern half of California's Central Valley between now and June.
And Daniel, it sounds like you're saying we don't even really need a lot of rain to do that. Just the snowmelt itself could produce that substantial flooding.
Yeah, I mean, at this point, there's so much snow water stored up there in the mountains that is eventually going to have to come downhill when it melts. That is on its own enough water to cause major flooding if it happens with any speed.
So really what we need to hope for is probably a cool, dry spring, right? With no major heat waves, no late season atmospheric rivers.
Essentially, yes. And then even then there's going to be flooding because it does still have to melt at some point. But hopefully it would do so in a most gradual fashion possible would probably be the best case outcome at this point.
Yeah. Daniel, you do a lot of engagement with people online. I saw you even do virtual office hours. I've never heard of anyone doing that. How can people find you online? I know a lot of our listeners are going to want to hear more about your insights in science.
Yeah, I'm pretty easy to find online. I'm active on Twitter. I'm at weather_west. I write the Weather West blog at weatherwest.com. And as you mentioned, I've recently ventured into producing my own video on YouTube, and I've been doing the most popular thing has been these live interactive weather and climate office hours. Usually there's a lot of engagement with this, which I think is great. And it's nice for me because I don't necessarily have to prepare a whole lot in advance. I can kind of just show up almost like real office hours and just answer people's questions. I usually have a bit of a monologue to start and then I just answer questions in the chat. So you can find me also at Weather West, no underscore on YouTube.
Well, it sounds like there's going to be a lot more interest in what's going on in the West as the snow melts. I know a lot of our listeners are going to want to tune in and hear what you have to say. So thank you so much for your insights, and we'll continue to follow your research and your insights online as well.
Great. Thank you.
Thank you, Daniel, for sharing those perspectives. Some really great science there. Our next guest is Andrew Schwartz, the lead scientist and station manager of the University of California, Berkeley Central Sierra Snow Lab. If you've been paying attention to extreme weather stories on the news, you've probably seen the Central Sierra Snow Lab quoted. The whole world has been watching them as they've been measuring this near record snowfall here in the Sierra. And Andrew, we're excited to talk to you on the podcast and get your perspectives on what this winter's been like.
Oh, thank you for having me on.
Andrew, hats off to you, doing great science under difficult situation. You're up there at the Central Sierra Snow Lab, close to 6,900 feet. I know it's difficult just doing the science up there, but you've been able to communicate with the world about what's happening. What's it been like to live and work in these circumstances?
It's been challenging. I mean, it is a snow lab, so we're used to the snow and the occasional big storm. But with that being said, these big winters like this one mean new challenges. We have to go out, and after every storm now, we're clearing snow from roofs, from instrumentation. We're having to literally dig out of the lab to make sure that we can get up and away from the entrance. So it's normal science, but with a lot of added backbreaking work.
It sounds like a lot of maintenance just to operate and live up there at that under those conditions.
That's absolutely right. Yeah, we have a number of different structures out here that continually need to be cleared. We have to make sure our backup generator is running in case the power goes out. And then on top of it, we are about 1,000 feet off of the main road, which means that when the snow does get really deep and it's really fluffy, we have to use the snowcat or snowmobile to get in. So we're also having to deal with the maintenance of those as well.
Wow. So even just the access points, all of that, you have to keep maintaining it.
Absolutely. Yeah. It's a lot of work, but fortunately, we've caught a little bit of a break in the storm systems coming through. So it's been a little bit lighter as of late, but another big one coming through today, actually.
Yeah. Andrew, could you tell us a little bit about the Central Sierra Snow Lab? Like, how long have records been kept? And then where does this winter fit into the long-term context of records at the station?
Yeah, so we have been in operation since 1946 when the Army Corps of Engineers and the then Weather Bureau, which is now the National Weather Service, built it. So most of our records here at the lab go back to 1946. In terms of the surrounding area, though, being here on Donner Summit, some of them go all the way back to 1878 when the Transcontinental Railroad began record taking in the region. So we've got a wealth of data up around this region, and because it was so important to being able to make it through safely or, unsafely in the case of the Donner Party and a few unfortunate others. But as far as things go with where this season racks up, effectively, we're a little over 57 feet of snowfall this year, which puts us squarely in second place of all time going back to 1946 here at the lab, with only the winter of 1951, 1952 beating it with about 68 feet of snow. So It's been one heck of a winter, but fortunately, we're not quite to the 1951 and 1952 levels yet.
Yeah, but here we are. It's still active. It's still snowing. It looks like, I think today, as we're recording this, you'll probably get over 700 inches for the year, right?
Absolutely. Yeah. We were only, I think, about 8 inches away from 700, and we're expecting about somewhere around 3 feet today. So we'll definitely surpass that 700. And then, it's not going to be quite as intense as late February and early March was up here. But it's looking like we do have storm systems that are going to continue to roll through. So I don't know if the 51-52 record is in jeopardy at this point, but it's certainly not out of the question that we could break it.
That is amazing. I mean, that's just, you said right now you're at about 57 feet of snow for the season. That's just hard for our listeners probably to even comprehend. I know it's hard for me to comprehend.
Yeah, it's a ridiculous amount of snowfall. I grew up in Colorado where 3 feet of snow over the course of 3 days would shut down Denver for days on end. And so, when we get 3 feet or 4 feet in a single day up here, and you get, 3 of those in a row, it's kind of surreal seeing that much snow come all at once. And just, trying to visualize how deep 57 feet actually is a little bit difficult too, it's effectively a 5-story building. Fortunately, it compresses over time. So there's only about 15 feet of snow on the ground now, but yeah, it's been a wild winter.
It's so far outside of our frame of reference. It's kind of hard to find context for it. Like you were saying, Andrew, can you walk us through like how you do the measurements? Like, is there a methodology to it? How frequently do you take measurements? How does that play out for you at the lab there?
Yeah, we have a number of different measurements that we do on a regular basis. The most important ones, the ones that tend to generate the biggest headlines are our daily snowfall measurements. So at 8 a.m. and 4 p.m. every day, we actually go out on days when it has or is snowing and get measurements of the fresh snowfall. So we go out and it's a really low tech, anyone can do it in their backyard. But we have what's called a snowboard or a snow interval board, which is just a piece of plywood, white plywood that we lay on top of the existing snow surface. And it's got a little pole attached to it so we know where we put it. And then snow builds up on that. And we go out there with a measuring tape, stick it down into the snow to get the depth of the snow in centimeters. And then we actually go through and take a little core of the snow using a hollow plastic tube to weigh it and get the amount of water content in it. So our board's relatively big. We actually get 4 separate measurements and then average them out so that we don't have any localized effects like drifting and things like that. And that's the most important one we do. But we also do things like our snow water equivalent with our federal samplers. So that's actually taking the amount of water in the snowpack itself and determining that. So if you were to melt the whole snowpack, this would be how much water is in it. And that is a giant metal tube that goes from the very tip of the snowpack all the way down to the soil underneath. So right now, those tubes are about 15 feet long. They're a little unwieldy right now, actually. But we do those as well because those keep track of our water resources. And then in addition to that, we have a whole suite of different instrumentation continually taking measurements up here as well.
Andrew, for the snow water equivalent, do you do that really just by weight or are you melting anything down?
That's primarily just by weight. So there's, I call them kind of glorified fish scales, the old school fish scales with springs in them. And that's basically what we use. We take the big sample out in this aluminum tube, and then weigh it in one of these scales. And the scales are actually calibrated to give inches of snow water equivalent. They're not in grams or ounces or anything. So it makes the conversion nice and easy.
Sure. Every time you do a measurement, say 8 a.m., 4 p.m., are you cleaning off the board then after that measurement?
That's exactly right. Yeah, we do that measurement, we clear it off completely, and then we do the next interval to get how much snow has fallen. And we've been doing that here, all the way since the lab opened in 46. So it's interesting to see how the snowfall amounts have changed over time, and the water content in them as well.
Yeah, I would imagine the water content's very important for hydrologists, for floodplain managers, things like that. People that are curious what may be coming with the meltwater, you need to know more than just the snow depth, right? You need to know really how much water is locked in up there, I would imagine.
Yeah, the new snow depth, that's exciting for people that want to go skiing. And it's fun because it's big numbers. But even like the snowpack depth itself, that's not really important in terms of the number that we all focus on in science and as water managers. That is the snow water equivalent. That's the bread and butter. So we tend not to focus on how deep it is or how much we've gotten, but rather how much water it's storing overall.
Yeah, that makes a lot of sense. I'd imagine a lot of different stakeholders are interested in your data. Do any really stand out to you, like the types of scientists or the types of professionals that are in contact with you or just using the data that you're putting out there?
Yeah, I mean, I think the thing that really stands out is just the variation and the wide range of different partners and collaborators that we do have. Our largest collaborator right now is the California Department of Water Resources. We test a lot of their new technologies for them, and then they also use our data. But we have partners at the National Weather Service. We have partners with the California Highway Patrol. We have partners with ski resorts. We're kind of all over the place, and they all love using our data a little bit. So it's kind of fun having such a large variety in who we're dealing with.
Andrew, I've seen you all like blowing up on media around the world as everyone's tracking. When this went from, just being a busy season to being a nearly record-breaking season, you're everywhere. How has that been, just keeping up with the email correspondence and social media while you're trying to take measurements and you're trying to just keep your facilities operating? Yeah,
it's challenging. But it's worthwhile too. One of the things that I've always been very into as a scientist is science communication, because ultimately, if we can't communicate what's going on with the science, then there's not a whole lot of point doing it. If only 3 people can understand what's going on. So, there are definitely times where I get overwhelmed and worn out. It gets hard because of the media onslaught and having and being able to relate this through social media. But that's also one of the reasons that this lab is so important, is to be able to do that. And so it does get tiring, I'm not going to lie, but it's very worthwhile. And to me, realistically, it's also one of the most rewarding parts too.
Sure. No, and it's very beneficial, obviously, to all these stakeholders and just people around the world that are tracking extreme weather and climate. Andrew, will y'all still be operating, say, into April and May? I mean, eventually there'll come a time where you're not really getting that much new snow, but what's happening in the snowpack is interesting as it starts to melt. Will you still be taking snow depth measurements or anything like that through the spring?
Absolutely, yeah. If there's snow on the ground, we're going to be getting measurements of it. And realistically now, at this point, it's likely that we'll see some of these patches of snow stick around until July or maybe even August, given how deep the year's been. So we're going to be up here regardless. And then even after the snow melts, we're putting in a brand new 25 sensor piece of equipment that I've dubbed the Sky to Stream measurement system. And that's going to take up some time too, because that's going to allow us to measure basically every aspect of snow and rain from the moment it falls out of the sky until it's running downstream into our reservoirs. And that's a really exciting project. And we'll have a live webcam installed as well, so people can see what it looks like up here on a regular basis. So we've got a lot going on and more coming for the future.
Yeah, that sounds fantastic. And I would imagine with a busy season like this, where it's not going to even melt until you'll probably still have snow up there into maybe very early summer. I would imagine at least late June. You might only have just a couple month window then to do that maintenance and add those new features until the next snow season starts.
That's exactly it. Yeah. We generally see our snowpack melt out around the end of May, but I think it's going to be around for at least another month, if not a month and a half longer than that.
Sure.
So yeah, we're going to have to cram a lot of work into a short time, I think.
Andrew, if people wanted to know a little bit about the snow history of the Sierras, like pre-1946, you mentioned with the Transcontinental Railroad going through, measurements were made. I mean, like, where could people find those types of resources?
Well, we have one of those plots on our website, cssl.berkeley.edu, and it's on the snowpack climatology page. It lists every measurement from 1878 until current. But also, there's a lot of records that we don't have on our website. So, for instance, there's what's known as a Donner Summit Snow Survey site or aerial site, and if you Google that, that'll bring you to the USDA page that'll have snow water equivalent measurements going very, very far back. And so, realistically speaking, we've got a lot of those records, but if there's something in particular that you're interested in with regards to snow or weather on the summit, generally Google's a great help because there's so many different federal agencies that have been working up here.
Yeah, I know a lot of people are watching you all over the world, because the most populated state in the union is really dependent on this snowpack, both for water resources and for potential flooding this spring. So I know a lot of partners are involved, and so that usually draws a lot of attention.
Absolutely, yeah. There's a large consortium of everyone that has to get together and figure out how to manage this water. And I think water in the Southwest U.S. is it's in a dire state. And this one season has been amazing, but it's not going to fix every issue. So yeah, it's kind of all of us scrambling to get the data and figure out what we can do with it and manage our water correctly moving forward.
Yeah, that is a great perspective. Andrew, any last things you'd like to share with our listeners? Any last big pictures or take-home points?
It's so rare that I get to be optimistic in this job because it's always about drought. So just that it's a good year and a year to be happy about as far as water resources in the Western U.S. So very exciting stuff there.
That's great. Well, Andrew, thank you so much for coming on the GeoTrek podcast. Lastly, how can our listeners find you? I mean, how can they find you online, find the research that y'all are doing?
Yeah, so we have, of course, our regular website, which I mentioned earlier. That's cssl.berkeley.edu. But we also have our Twitter page, which is at UCB_CSSL, a Facebook page, which is UCB.CSSL. And then realistically speaking, if there's a few other pages that we run as well, and just by Googling the Central Sierra Snow Lab, there's plenty to learn about. And I encourage anyone that wants to reach out to do so.
Awesome. Thank you, Andrew. Best wishes the rest of the spring season as we wrap up the snow and get into more of the melt season. We'll be following you online, and great work you're doing up there, and really appreciate you taking a little time to come on the GeoTrek podcast.
No problem at all. Thanks for having me, Hal.
Thanks, Andrew. Wow, it's just amazing to picture what you've lived through this winter with snowstorm after snowstorm up there high in the Sierra. Our final guest is Julie Kalansky. She's the Deputy Director of CW3E and a climate scientist at Scripps Institute of Oceanography in San Diego. She's also the program manager for the California-Nevada CNAP program. This is part of the NOAA RISA program. They are all over the country really doing applied climatology and some very great work that's bridging the gap between climate science and the people that the science impacts. Julie, really great to have you here on the GeoTrek podcast.
Thanks for having me.
Julie, and you have a lot going on out there. You're program manager for the California Nevada Climate Applications Program, which is one of these NOAA RISA programs, which focus very much on applied research with climatology, extreme weather. And y'all in that region kind of went from extreme drought to like this crazy winter with floods and mega snowpack. What kind of a ride was that like for you to go from one extreme to the other?
Yeah, it has been. I mean, and also at the beginning of the year, given that it was La Nina, a lot of the extended range forecasts were predicting at least normal or drier, not this really extreme wet year. And so, and early in the season, October, November, and even most of December, that is, we didn't have any of those big events. And then it started in December with those family of 9 atmospheric rivers that, started right after Christmas and went through into mid-January. And then thinking about that, also the experience of the previous year where we had a really wet fall and then, a very extremely dry January, February, and March. There was some hesitation to, thinking about, that was a lot. And there was definitely some flooding in locations, but if that was it, what would that mean in terms of drought mitigation? But then it started, we got the additional storms in end of February and atmospheric rivers into March. And so now there's this massive snowpack. Unfortunately, it has been a relatively cold winter in looking at climatology, which has helped retain the snowpack. And a lot of that precipitation it didn't all come down at once as rain, because the flooding implications could have been much worse, although, there were some very impactful flooding, and the emphasis on those impacts, I don't want to in any way belittle those, but it could have been much worse if it wasn't as cold. These storms weren't as cold as they were. But now we're looking at, the huge snowpack, the potential development of the Tulare Lake, which hasn't happened, in decades. and where all that snowpack will go, and how to use the water that's there for recharging groundwater as much as possible, and also to prevent flooding as it comes down, because there's just so much.
Julie, as this tremendous snowpack melts, what are the geographic areas that concern you the most for potential flooding?
It's a lot in the San Joaquin Basin, and particularly the southern San Joaquin Basin, and off the Kings River, Kern River, where the Tulare Lake bed was historically.
I understand. So it's a lot of really those areas kind of coming into the southern San Joaquin that are just, from what I've heard, even if it's a gradual melt, it's still going to be really high, and there will be flood impacts almost for sure.
Yeah, I think that, the best that we can hope for is that it stays relatively cool. We don't get any large heat waves or anything like that, that it is as slow as possible to mitigate that flooding. But there's just so much that I think there is the anticipation that there will be flooding in certain areas.
Julie, could you walk us through, for most of the last decade, the big issues with water in the West has been drought and just not enough water. Now, all of a sudden, we've had flooding rains and then this tremendous snowpack that's going to melt. Are there ways to store some of this water to help relieve drought? Or for the most part, is that just going to kind of flow through the state, and is the focus just on preventing flood? How do we manage this? How does the state of California, or how do the stakeholders in California manage these complex resources?
So I think there's an acknowledgement within California that, so we know that we have the most highly variable precipitation year to year of anywhere in the US. And so although we've been managing for a lot of droughts, there has been some really wet years, thinking of 2017, 2019, where there was flooding throughout the state, and then, a 3-year drought, and then this year. So it's really this back and forth between wet and dry years that the state, regionally, locally, everyone has to manage for. And I think there is, especially because there's been so much of this back and forth between extreme wet and extreme dry recently, there's a awareness of this is something that, it's not having to manage for both at the same time and do the best to manage for flood and drought. And they're really these two sides of the same coin. It's really the frequency, the timing, the magnitude of large storms in terms of determining wet or dry. And so I think, the state has, and locally the state has started the Groundwater Sustainability Act in terms of the last drought, which looks at how we can use groundwater and surface flows to help mitigate drought impacts. And this is the idea of, when it is a wet year, where can you recharge some of that groundwater? And so look at groundwater and surface water together, and not just one or the other. And so that's something that is actively ongoing, and there's still some research to be done in terms of impacts, but there was an executive order this year to help allow for more recharge without going through certain permitting processes. So, and I would say, I think there is also just understanding that while also dealing with all the flood, that there's going to be another drought, whether it's next year or in 2 years, we're going to be faced with another one. And I think there is a broad understanding that it's going to happen. And so how can the water that we have now, I think first is to reduce flood risk and mitigate lives and property, and want to make sure that people are as safe as possible. But then the other part is how do you mitigate for the next drought, whenever that may come.
Yeah, and you brought up a good point that fighting against drought not only has to do with maybe retaining some of these water in reservoirs, but also recharging groundwater in aquifers.
Right. Yeah. So I think that's something that came to the forefront really during the 2014-2016 drought, or 2012-2016 drought, is the combined use of both surface and groundwater, and how to look at the system more holistically.
Yeah, Julie, so CNAP obviously doing a lot of applied research with looking at climate impacts and how stakeholders can make better decisions. Will there be, moving ahead in this next year, what kind of projects will you all be working on?
So we have one project that I'm really excited about that's with Bakersfield Community College. And the idea is to bring in climate and water resiliency to Kern County, which is in Bakersfield is part of that. And so be looking at working with a researcher at UC Merced who has a model to look at, different climate scenarios and also various different groundwater scenarios and what that means for water. With another researcher at Scripps looking at, agricultural productivity and water use and linking those. And then by working with the community college faculty, able to develop curriculum that gets integrated into the classes and kind of brings that capacity and knowledge regionally focused on water resiliency as climate is changing and we are experiencing these climate extremes.
Well, it sounds like a lot of different stakeholders involved at different levels, right? The community level, the agricultural level, just a lot of these different sectors. And that's great that you're engaged with them so well.
Yeah. And the other thing we have been doing, this is with NIDIS, which is the National Integrated Drought Information System, has been sending out monthly drought status updates. And so just to, are we still in a drought, or what regions are most impacted, or where has it been mitigated? And so to try and help with that clarity using, showing that kind of regional, both California and Nevada impacts.
Julie, to what extent could drought return this year? And then I've been in California for the last week or so, just doing research on the ground. And some people have talked about, while this is temporary relief for forest fires, they're concerned there may be a lot more fuels that grow, a lot of underbrush and vegetation that if a dry period, comes later this year or next year, there could be a lot more fuels out there to burn.
Yeah, I think fire risk is always is something that we always contend with the Mediterranean climate, even though, this is a really wet winter, the potential for, warm summers, when you have low humidity, high winds, you have these fire weather conditions. And so that is, the one thing is if, this year has been relatively cool, if the snow stays on the ground a little bit longer, it might delay the start of the fire season. But once we get into that fall times, especially when you think of downslope winds, like the Diablo winds or the Santa Ana winds, that fire risks exist every year. It's something that we just contend with.
The concern is especially like late September, October, getting into early, astronomical autumn, right? Right. With you've already experienced the long summer. And like you said, some of these downslope wind events can be very dry and very bad fire conditions.
Correct. Yeah.
Julie, any last things you'd want to share with our listeners just about what you're working with out here, what you're dealing with out here, what the state, well, really you're working with Nevada and California. Just any last thoughts to share with our listeners?
I think it's I would say I feel very fortunate to be working in the regions and within California and Nevada. I think California is very proactive in thinking about climate adaptation and what can the state do, but then also support at the local level to think about what are those adaptations or changes that need to be made to build resiliency to these challenges, flood, drought, fire weather, all of these.
Yeah, and like you said, the region has so many different hazards. I was up at about 7,000 feet in one of these communities with 10, 12 feet of snow on the ground. And I was talking to a resident about building codes for heavy snow loads. He said, we also have to build for earthquakes at the same time. So I was like, wow, that wasn't even on my radar. You're all these different multi-hazards in the most populated state, obviously a lot of impacts, and just really appreciate what you all are doing just to get out there and engage with people.
Yeah. Well, thank you. Thanks for having me today and giving me a chance to talk about it.
Yeah. Julie, how can our listeners find you online? How can they find your program? If people wanted to look you up and see what's going on and learn more about your research.
So we do have a webpage, which is cnapcnap.ucsd.ucsandiego.edu, where it highlights some of our different projects. Another one is, like I mentioned, with the drought status updates is through NIDIS, NIDIS, the California and Nevada dues, and they can sign up for the mailing list, which these drought status updates go through.
Great. Thank you so much, Julie. Best wishes as we pull out of this very wet winter. We'll have to see what the spring and summer hold ahead. We'll be following you online. And thank you so much for taking time to come on the GeoTrek podcast.
Great. Thanks so much for having me.
Thank you, Julie, for sharing those perspectives. Wow, this was a lot of information we covered here. 3 very extremely prolific scientists sharing their perspectives with us today. I know our listeners are really going to enjoy this episode. I often on the podcast try to look back and give some insights on what our guest had shared. We had 3 heavyweight guests today. They shared a ton of information. So I'll make my perspectives very short, just one perspective, one thought from each of the researchers. I thought it was really interesting that Daniel mentioned that we normally would have expected a drier than normal winter because we were in La Nina. And I thought that was interesting. These teleconnections, these climate patterns, these indices, they give us probabilities, but not guarantees. And so although we would have been normally expecting a drier than normal winter out west, we actually got a much wetter than normal winter. And, we saw this too with last hurricane season, right? We were expecting a very active season. It ended up being pretty normal by the numbers, which was a little surprising because, again, it was a La Nina year. And in part, that usually indicates more hurricane activity in the Atlantic basin. So just a reminder that these indices, these climate patterns, they don't provide guarantees. They just provide probabilities. But sometimes the climate system does not follow along with those probabilities. So thanks for sharing that, Daniel. I thought that was really interesting. Andrew, thank you so much for sharing your perspectives. Something that you said got me thinking about why we have the climate records we have. It's not random. It's often based on geography and on history. The Central Sierra has some of the best mountain snow climatology anywhere on Earth, and that's not by mistake. That area was a very popular migration path with the wagons coming through in the 1800s. Eventually, the Transcontinental Railroad came through that area. And today, I-80, if you're getting on I-80 in New York City and you keep going west, you eventually get to San Francisco. You go right through there by Donner Pass and Donner Summit, that area that has these incredible snow records back for a long time. And so Andrew's perspective on this got me thinking about why we have those records where we have them. I'm very thankful that we have a very long record there at the Central Sierra Snow Lab that enables us to really build a good climatology and to put a winter like this winter into context. And Julie, thank you so much for your perspectives. You got me thinking about California, just such a multi-hazard area. Not only does it have the highest population of any state, so there are a lot of impacts if something does happen, but y'all are dealing with drought, wildfire, mega snow up high, floods, mudslides, avalanches, the list goes on and on, even a lot of coastal things with sea level rise, coastal erosion. There's so many things that happen in the meteorological side of things. And then I was, I was talking to a homeowner up high who said, oh, not only do we have to build for heavy snow loads, but also for earthquakes. So it's like, wow, they just have so many hazards out in California. And so that's really unusual compared to a lot of other states really just maybe face 1 or 2 things. California, y'all are facing a lot of different hazards. And something new that I did not realize, I didn't know that California has the greatest variability in precipitation of any state. It makes sense. We have already starting with a Mediterranean climate that has a wet and dry season, but then it seems like you get these prolonged, at least, 1 or multiple years sometimes of wet patterns or dry patterns. It seems like you can get some very severe drought and wildfires, or you can also get a lot of floods and a lot of impacts from hydrology as well. So thanks for sharing that. And thanks to all of our guests that came on the podcast and made this a very interesting episode. I've been asked a lot of questions about these atmospheric rivers, about what's going to happen when the snow melts. A lot of these questions during my trip came my way. This is great to be able to direct them to the experts that study this stuff every day. Thank you so much for taking time to come on the podcast. And don't miss out on next week's episode. It's going to be part 2 of a 2-part series here in California. Next week, we're going to have some conversations just with random people I talk to. Also with first responders, we're going to talk to architects and engineers that build for heavy snow loads and that talk about what we've learned this winter and how we can apply that to the built environment to reduce our losses and mitigate, our loss of life and property moving ahead. It's always good to learn from these extreme weather events, and we definitely wanted to learn from this one. So don't miss out on the next podcast, which will be part 2 in this 2-part series focused on the mega winter in California. Thanks for coming along on the adventure, everyone, and thanks for following us online. I know we have our Facebook group, GeoTrek the Community, and we've been very active, very engaging throughout our travels with GeoTrek and connecting people to our guests as well. Everyone, thanks for tuning in, and we'll catch you at the next episode of the GeoTrek podcast.